So the idea behind a logarithm, let's look for a minute at just the graph of y equals 2 to the x. So we know that when x is 0, we're going to get 1 because 2 to the 0 is 1. So it's going to contain the 0.01. We know it's going to be our typical exponential growth function. So it's going to look something like that. It's going to rise from left to right. It's going to have a horizontal asymptote at y equals 0. Now, using the ideas that we talked about before, we can see that this is clearly a function because it's going to pass the vertical line test for functions. It's also what we would call a one-to-one function because a horizontal line will only intersect this in exactly one point as well. So what that means is that it must have an inverse that is a function as well. And so you can sort of see what that inverse is going to look like if you switch the ordered pair. So if 0, 1 is an ordered pair on the original function, then 1, 0 must be an ordered pair on the inverse of that. If y equals 0 is going to be a horizontal asymptote for the original function, when we switch the x and y, then x equals 0 is going to be a vertical asymptote for the inverse function. And maybe we can just plot one more point so we can get the idea. If we plug in 1 into the x for 2 to the x, we'll get 2. So 1, 2 is a point on the original function, which means if we switch the x and y around, I'm going to move the 1, 0 over here, and 2, 1 is going to be a point on the inverse function. And we could do more of it, but what we're going to get then is something that looks like this. And as is true with all inverses, they are reflections of each other in the line y equals x. So that is, if you look at that line that goes through the origin at a 45-degree angle, if you draw the original 2 to the x in really wet ink, fold on the dotted line, the imprint is going to be the inverse. Or another way of thinking it, if you draw both and you fold on the dotted line, they're going to land right on top of each other. Okay. So what we call then, so this is what it looks like. We know that whatever ordered pair we get for 2 to the x, its inverse is going to switch those. And the name of that inverse we call a logarithm base 2 of x. So the base of the exponential is 2. The base of the logarithm is also 2. Now, as is true with all functions and their inverses, on the original 2 to the x, we can see its domain, the values of x that we use, is what? All real numbers. Good. And its range, that is the y values that you get once you plug in all of those real numbers.
All real numbers greater than 0?
Exactly. So I'm going to say y greater than 0. So it's never actually equal to 0 because it approaches that horizontal axis but doesn't ever touch it. So that means that if we look at the inverse function, that logarithm base 2 of x, then what we would expect from its domain and range, which hopefully is borne out by looking at the graph of it, the domain of the logarithm, the x values that get used are x just greater than 0. And remember, we talked about that when we were talking about restricted domain functions, that things that have a 0 in the denominator have a restricted domain, square roots have a restricted domain, and logarithms have a restricted domain as well. And the range of this logarithm is all real numbers. So even though it grows very slow, so just as an exponential grows really, really fast, it gets big in a hurry, a logarithm is a very slow growing function. So it takes a long time to get there, but there is no limit to how high it's going to be. There is no horizontal asymptote there. Okay, so we have this fundamental relationship. This is really key to the the equivalence between a logarithm and an exponential. So if we have y equals the logarithm base b of x, that's a logarithmic equation, and we can convert any logarithmic equation into an equivalent exponential equation if we say, and hopefully you know this, b, the base, raised to the y power is going to equal x. So a logarithm can become an exponential can become an equivalent logarithm. Okay, so notice that for one thing, and I'll say this many times over, a logarithm is an exponent. A logarithm is an exponent that you raise the base to in order to get that number there. A logarithm is an exponent that you raise the base to in order to get that number. So let's do a couple just conversions first. So I'm going to give you a logarithmic equation and you write it as the equivalent exponential. So you go from left to right. Then I'll give you an exponential equation and you write it as the equivalent logarithmic equation. So if we say that 10 to the third is equal to 1,000, true statement, then you can write that equivalently as the logarithm base 10 of, it's going to equal it'll equal the exponent, so it's going to be of 1,000 is equal to the 3.
Isn't there a thing for log base 10?
And there is a thing that a logarithm base 10, because this is used so often, we don't have to write that subscript. And so that's known as a common logarithm. We have one other where we can do that. What's that? Yeah, so a logarithm base Euler's number is also used a ton. And so that is written as just ln x. And that is known as a natural logarithm. All others have to have that subscript, that base written. Okay, let me give you a logarithmic equation and you write the corresponding exponential. So we'll say logarithm base 2 of 8 equals, I did that already. Hold on, let me give you a different one. I want to go the other way. Let's say 16 to the 3/4 power is equal to 8. So there's an exponential. And so you can write that as a corresponding logarithmic equation. So we would say it's a logarithm. Logarithm base what? 16 of 8 equals 3/4. Okay, let me give you one the other way. I'll give you a logarithmic equation. So a logarithm base 25 of 1/5 is equal to a negative 1/2. So the corresponding exponential that make sense? Okay. So now we're going to use this idea of converting back and forth to solve some logarithmic equations. And these are you're going to have to do without a calculator. So I'm going to say solve and no calculator. So that means these have been carefully constructed so we can actually do them, because tomorrow we'll talk about how to solve equations using where we have to use our calculator. But this is just trying to emphasize this relationship. So I'm going to put 3 of them down here because I'm going to move the x to these different positions, and we have to be able to solve equations no matter where that x appears. So sometimes people find one or more of these more difficult than the others. So they're kind of a little different twist to them. I think this last one tends to be one that can bother people. So you notice here we have in this whole logarithm base b of x equals y. We put that x in the position where the y was, and then where the number is, and then where it's actually the base. So same strategy to start with. We're going to always start by writing the equivalent exponential equation. So in the first one, the equivalent exponential equation is going to be 2 to the x equals 32. Exactly. That makes sense? So that's how they're going to start all the time. And now we want to make these two equal to each other as powers of the same base. So 32 is a power of 2. It's 2 to the, count with me, 2 times 2 is? So it's going to be all the way up to 5. So it's going to be 2 to the 5th. And so then if two powers of the same base are equal to each other, then we know their exponents must be equal. Make sense? Okay. Next one, we're going to get, waiting for it. Good. Now the x is already by itself there. All we have to do is figure out what is 3 to the negative 4. So the negative part of the exponent is going to make it a fraction. And now when you have 4 3's being multiplied, if you group them and you multiply the first two together and get 9, then the last two together get 9, then you can just multiply the 9 times 9, and that's going to be 1 over 81. That's the easier way to go, since you can't use your calculator. Okay, what's the equation we get here, the exponential? Now, these are the ones that people seem to have the most trouble with. We're trying to solve this now for x. So we got out of the logarithm by writing the corresponding exponential. Now we're trying to solve this equation for x. So we have to get rid of this exponent negative 4/5. And to do that, what are we going to do? We're going to raise it to the reciprocal power. Because when you raise a power to power, we get to multiply those exponents. So the reciprocal of negative 4/5 is a negative 5/4. And then we have to do the same thing to the other side of the equal sign. So this, what we see by the x is what drives what we're going to do. And then once we do that, the x is just by itself because you multiply those exponents. Negative 4/5 times negative 5/4 is a positive 1. The challenge then is how do you simplify 16 to the negative 5/4? And 16 is a power of 2. It is 2 to the 4th. And when you raise that to the negative 5/4, we can multiply those exponents. The 4's will cancel. And so we're looking at 2 to the negative 5. You with me? Which is 1 over 2 to the 5th. And we said 2 to the 5th was 32. So we get 1 over 32. Okay? So we talked about common logs. We talked about natural logs. Let's talk about some properties of exponents. There's really only 3 of them. Properties of logarithms, rather. So there's really only 3 of them. They're pretty important. So the first one is that the log any base of x times y is the log of x plus the log of y. And the second one is the log any base of x divided by y is the log of the numerator minus the log of the denominator. And the one we will make great use of tomorrow is the log of an exponent is the exponent times the log. So you're allowed to bring that exponent out in front. I'm racing against the clock, which is why I'm doing this kind of quick. Things to note, because an exponential and a logarithm are inverses of each other, this looks really weird. But if we take b raised to a logarithm base b of x, an exponential base b and a logarithm base b are inverses, they're going to cancel each other out and just give you x. Similarly, the logarithm base b of b to the x, again, logarithm, exponential are inverses. We'll talk more about that in the days to come. All right, very good.